Adding, subtracting, and multiplying complex numbers. A complex number is any number that can be written in the form a plus bi, where a and b are real numbers. This means that 5 is a complex number because 5 is equal to 5 plus 0i. It also means that 3i is a complex number because 3i is equal to 0 plus 3i. And of course, 5 plus 3i is a complex number too. It's worth noting that the set of real numbers is included in the set of complex numbers a plus bi, and it happens when b is equal to 0. And also, the set of pure imaginary numbers is included in the set of complex numbers a plus bi. This means that a equals 0 and b cannot equal 0. Now that we have expanded our knowledge of numbers to include imaginary and complex numbers, the Venn diagram shown below represents these new sets of numbers. Our innermost set of numbers is our natural numbers, or our counting numbers, so counting from 1, 2, 3, 4, all the way up, and it keeps on going. Our whole numbers are the natural numbers and the number 0. Integers are the whole numbers and their opposites. So we not only have 0, 1, 2, and keep on going, we also have -1, -2, and we keep going in the negative direction. We then have rational numbers, which consist of integers and any fractions or decimals that result in fractions. We then have real algebraic numbers, which include our square roots and expressions that include square roots in them. And then we have real numbers in general that also includes our transcendental numbers, such as e, pi, and so on. And then outside of the real numbers, we now have complex numbers, denoted by capital C. And another part of complex numbers is the imaginary numbers. Note that imaginary numbers are not connected to the real numbers, but both the real numbers and the imaginary numbers are both a part of the complex number system. Now that we've been introduced to complex numbers, let's talk about their standard form. The a plus bi form of a complex number, where a and b are real numbers, is known as the standard form or component form. The real part, or real component a, is listed first, followed by the imaginary part, or imaginary component bi. And here are some examples. In the complex number 3 plus 2i, the real component is 3 and the imaginary component is 2i. In the complex number 8, it only contains the real component of 8 and 0i as the imaginary component. In the complex number -6i, this time the real component is 0 and the imaginary component is -6i. And in the complex number 1/3 plus 5i, the real component is 1/3 and the imaginary component is 5i. There is nothing surprising when adding or subtracting complex numbers. The number I commutes and distributes just like any real number, so the arithmetic of complex numbers looks very much like the arithmetic of real numbers. You could also consider it to be very similar to operations with polynomials. The only exception that we have to this rule or these similarities is that I squared is equal to -1. So when you're adding, say, a plus bi and c plus di, you would add together the real components a plus c, and then you would add together the imaginary components bi plus di. You can factor an I out of both of those, so that's how we get the coefficient being b plus d, and then you'll have the I afterwards. Subtraction is very similar. The difference is, though, you should remember, again, think of it as subtracting polynomials. We have this hidden -1 there that we can distribute through that will help us rewrite and combine our like terms. So we would have a minus c as the real component, and then we would have plus bi minus di. And then if you factor the I out of both terms, you would then have b minus d in parentheses and I outside of them. Let's try using these properties for exercises A and B. So first we have 7 plus 4i plus 3 minus 2i. If we rearrange it and put our real components first, we would have 7 plus 3, and then we would have plus our imaginary components 4i minus 2i. And then when we do simplify these, we would end up having 10 plus 2i as our final answer. Now let's look at exercise B. In this case, we have 4 plus 3i and then minus the quantity 5 minus 6i. So remember, we have to put our -1 in its position and distribute it through. So we have 4 plus 3i minus 5 and then plus 6i. And the reason we get that is because -1 times -6i will give us positive 6i. And now if we rearrange them and put our real components first, we will have 4 minus 5, and then we would have plus 3i plus 6i. And then when we combine these together, the final answer will be -1 plus 9i. So when adding and subtracting complex numbers, combine like terms and leave answers in standard form. And here we see the solutions to exercises A and B, and they do match the solutions that we just found. Here are some more exercises that we can work through. In exercise C, we are adding together 5 minus 6i and 4 plus 8i. So since this is addition, it is simply combining like terms. So we have 5 plus 4 plus, then we have -6i plus 8i. And that will give us as our final answer 9 plus 2i. Now let's look at the next problem. This time we have subtraction in exercise D. We have 12 plus 3i minus the quantity 12 minus 3i. Some of you may think that the 3i's go away and 12 minus 12 is 0. Well, let's actually remember that we need to take this -1 and distribute it through. So we still have 12 plus 3i in the first set of parentheses, but then we have minus 12, and then -1 times -3i is positive 3i. And then if we combine our like terms together here, I agree that the positive 12 and -12, or that 12 minus 12 does equal 0, but now we have 3i plus 3i, which ends up simplifying to 6i. And here are the solutions to exercises C and D, and they do match the solutions that we found when we worked them out. When multiplying pure imaginary numbers, some simplification is required. Let's actually see what we're talking about in exercise E. We have to multiply 7i times 3i times 2i. And again, it's very similar to multiplying polynomials together. In this case, they're all monomials. So we would take the 7, 3, and 2 and multiply them together, and that would be 42. And then we have I times I times I, that's I cubed, or I to the third power. And then if we simplify I to the third, it ends up becoming I squared times I, and we still have the 42 out in front, and I squared is -1. So we'll have -1 times 42, which is -42i, as our final answer. And here we see the solution to exercise E, -42i, and it does match the solution that we found. Also, when multiplying complex numbers, the process resembles the multiplication of two binomials, sometimes known as FOIL. So if you had a plus bi times c plus di, you would have to multiply a and c together. Then you'd have to multiply a times di together. Then you would do bi times c, or b times c times I. And then you would multiply b times d times I, which is b times d times I squared. and I squared is negative 1, so then you would have negative BD or minus BD. And then we can see that we have two real components, AC and then minus BD. So they become, you bring them together to get your real part, and then you would have ADI plus BCI. If you put them next to one another and then factor out the imaginary variable I, you would then have AD plus BC, that's your coefficient, and your I for the imaginary number. Now let's practice multiplying complex numbers with these two exercises. Our first one, exercise F, mimics multiplying a monomial times a binomial. And we're going to use the same properties. We just have to remember that I squared at the end is equal to negative 1. So let's take the 2i that's out in front and distribute it through. And when we do that, we will end up getting 6i minus 4 times 2 is 8, and then we have an I squared. Well, I squared is negative 1, so we have 6i minus negative 8, and then the minus negative becomes plus a positive, and then if we put our real part first, that's going to be the 8, and then 6i is the imaginary part. So here's our final complex number. Now let's look at the next problem. We have 4 minus 3i, that entire binomial quantity squared. Remember, squaring in this case does not mean that you distribute the square to both terms and that's it. You actually have to either remember the rule for having a binomial squared or write the binomial times itself. So 4 minus 3i times 4 minus 3i. Like write it down twice and then apply the distributive property a couple of times, which is also known as FOIL. So we would have 4 times 4 is 16. 4 times negative 3i would end up giving us negative 12i, so we will subtract 12i. And then we're going to take negative 3i times 4. That would give us negative 12i again. And when we do the last part, negative 3i times negative 3i, we get positive 9i squared. Okay, well, this is plus 9 times negative 1. We can then also combine these two together. So we'll have minus 24i, and then we have the 16 that we can bring down from our first term. So now we have 16 minus 24i minus 9, and we can combine these two together, and that will give us 7 minus 24i as our final answer. And here we see the solutions to exercises F and G, and they do match the solutions that we found. 8 plus 6i for exercise F, and for G is 7 minus 24i. Here are another two exercises that we are going to simplify by performing the indicated operation, combining like terms, and writing our result in standard form. So in our first one, we have 3 minus 2i times 4 plus i. So we're going to distribute first the 3 through to both terms. So we'll have 12 plus 3i, and then we're going to take minus 2i, or the negative 2i, and distribute it to both terms here. So we'll have minus 8i, and then minus 2i squared. So we have 12. These two terms can be combined together. So we'll have minus 5i, and then we'll have minus 2 times negative 1. Well, 2 times negative 1 is negative 2, and minusing a negative is the same as adding a positive. So then we can combine our 12 and our 2 together to give us 14, and then we still have minus 5i for our imaginary component of this complex number. Okay, now let's look at exercise I. We have 4 minus 5i times 4 plus 5i. So we can distribute the first 4 through, and we'll end up getting 16 plus 20i. and then we'll take the minus 5i and distribute it through to both terms. So we'll have minus 20i minus 25i squared. Notice our plus 20i and minus 20i, they cancel one another out, so we have 16 minus 25 times I squared is negative 1. So we have minus a negative, that'll turn into plus a positive. So now if we add these together, 16 plus 25, we'll end up getting 41. And here we can see the solutions to exercises H and I, and they do match the solutions that we found. 14 minus 5i for exercise H, and 41 as the solution to exercise I.